We're now going to consider an infinitely long coaxial transmission line. And so we're not actually going to go through the process of using our Ampere circuit law, rather we're just going to look at the final result, but we're going to sort of talk about some of the key points of that final result. And so in considering this, we're going to look at two concentric cylinders with an axis along the z-axis and uniform current distribution. So I have this drawn here, so note over here our z-axis is pointing out towards us. So we have these two conductors. In the middle we have this blue conductor with current I coming out at us. And so that inner conductor has a radius of A. And then we have our outer conductor, which is this sort of cylindrical shell, which has our current going back into the page. And we see that it has some thickness T, and we have that the distance from the center to sort of the inner part of that hollow cylinder is a distance of B. And so again, we're not going to go through the whole process of solving for our H in all parts, but if we wanted to define H everywhere, we can think about how many Amperian paths we would need, and we can at least set those up and talk about it. So let's say to fully define our H, we would need 4 Amperian paths. So to fully define H at any point in space, we need 4 Amperian paths. And so let me capitalize Amperian. Okay. So what are our 4 Amperian paths going to look like? Well, we're going to need one in each of our two conductors. We're going to need one outside of both conductors and one in between the conductors. So let's say we have one in here like this, and so this is going to be in this direction, so we can call this our Amperian path L1. We also need an Amperian path which is in this outer conductor. So let's get that and get that roughly centered there. We're also going to need an Amperian path, oops. All right, so we're going to need an Amperian path which is in between our two conductors. And we're going to need an Amperian path which is outside of our two conductors. And so with all of those pieces of information, we could then find our H everywhere. And so let me go ahead and put directions and labels on each of these as well. So this could be our Amperian path L2. This could be our L3 inside that outer conductor, and this would be L4. And so again, the basic process would be the same as what we saw for our filament, in that we're setting up that integral equation, and because our H is going to be constant along any one of these Amperian paths, we can pull it out of the integral, and we're then left with just doing the integral along that path of the dl. Okay, so again, we're not going to go through this. If you want to see sort of more details about how to solve for this, you can look on pages 312 to 314 in the textbook, but the end result is that we're going to have different H in each of those 4 regions. So our H, our magnetic field intensity, is going to be equal to, depending on the region, something different. So let's talk about first that inner conductor. So for our rho, and so I'm going to define rho as being sort of the perpendicular distance from that coaxial cable. So remember, we're sort of looking at this head on, but if we think about, some point P out here, it would be some perpendicular distance rho from the center of our coaxial cable. So some perpendicular distance rho. Okay, so in the first region, which is going to be inside this first conductor, let me switch that. So inside this first conductor here, what we're going to see is that our H is equal to I times rho divided by 2 pi A squared in our phi direction. And now again, in this case, our phi is going to line up with our cylindrical phi, but in general, that's going to be locally defined, just like we saw previously with our infinite filament. And so that's going to be for rho values between 0 and A. And so what we can see is that our magnetic field intensity is increasing as we're getting closer to the edge of that inner conductor, and so that would be expected because as we're getting larger, as we're sort of getting towards the edge with our rho value, we're enclosing more current, so we would expect to have more magnetic field intensity. So the second region is this region in between our two conductors, and so the expression for that becomes I divided by 2 pi rho in our phi direction. And so this is again going to be for rho between A and B as we have it defined above. And so that looks pretty familiar. So that's actually the expression right here for our infinite filament. And so that makes sense because if we come up here and we look at this path L2, it's enclosing current I in an infinite filament A. So exactly the same, because again this is infinitely long. So exactly the same as our infinite filament problem, so as to be expected. So now let's look at this third case, and so I can't highlight inside there for some reason, but this third case which is inside this outer conductor. So we're looking along path L3. And so the result for that ends up being a little bit more complicated. So we have I over 2 pi rho out front, and now we're going to be multiplying that by the quantity of 1 minus rho squared minus b squared divided by t squared, which was the thickness of that outer conductor, plus 2bt. And so again, this is going to be for values of rho between b and b plus t. So b plus that thickness of that outer conductor. And so what we see here, again, we need to keep in mind for a given configuration, the b and the t values, so t and b are going to be some fixed values, and our rho is what's changing as we're sort of moving further out along that conductor. And so what we see then is that this is going to be fixed, these are going to be fixed, and ultimately as our rho is increasing now, so as this rho is increasing, we're actually decreasing our overall h because that term is being subtracted. And so again, that makes sense because that's sort of counteracting the current that's coming out at us in the inner conductor. So we have some current coming out of the page from the inner conductor, and we have some current going into the page. So as we're including more of this conductor, the current in the outer conductor, that's canceling out more of that current in the inner conductor. So let's now move on to talk about our final region, which is anywhere outside of our coaxial cable. So it turns out that if we're outside of our coaxial cable, we're just going to have 0 magnetic field intensity. So this is for rho greater than or equal to b plus t, so b plus the thickness of that outer conductor. And so if we think about it from our basic equation, that makes sense because remember our I enclosed is equal to the integral of some closed path of h dot dl. And if we look at this conductor and we say we have some current I coming out here and some current I coming in there, well, if we enclose both of those conductors with this path L4, for instance, we have current I coming out, current I going in. Because they're in opposite directions, they'll cancel out, and our net current enclosed is 0. So therefore, our H, if this is 0, then our H, of course, has to be 0 as well. And so that's what we see here. So again, our currents are canceling out, so we have 0 enclosed current, which means that our H is 0 as well. And so this is one advantage of using that coaxial type structure to send signals or currents sort of in both directions. We can sort of shield some of that magnetic field to other external equipment.